to get me the sheets that you have done. Just give it to me by random class. But right now you can keep it with you. So the question is, did anybody have trouble with mutual exclusion propagation? Okay. Did anybody have trouble figuring out the quadratic planning graph idea? So what's the problem with it? You did not figure it out at all. Okay. So I understand. Actually, the interesting part about this is there is a 4-page paper that I'll probably refer you to that got published in 2009. The paper that you saw was 2003, and it's actually a very interesting paper because that's a kind of a treasure trove of ideas, because they also talk about a planning graph based. I mean, if you looked at beyond the second page, you would have seen that they talk about planning graph based landmark computation. And in fact, theirs is pretty much the only systematic approach. And the stuff that you did in 2008, the 2008 paper that you read, it just gives some heuristic approaches for finding some causal, some landmarks. And these guys have a more systematic approach for finding it. And I think in 2003 idea and the quadratic planning graph idea got used again. I think the quadratic planning graph idea got rediscovered under the guise of essentially polynomial planning graphs. So the simple idea, obviously there are, I guess you got stuck because the description is too short and maybe you wanted more detail as to exactly what nodes to put in. But their simple idea is that once you have the normal planning graph, right, including the persist actions, then a quadratic planning graph essentially adds a bunch of quadratic actions, that is pair actions. The pair actions correspond to both real actions. Let's say if you have action A1 and action A2 appearing here, you will also have action A1, A2, which you will try to put in as long as they are not statically mutex. And if you do put them in, then the effects of this A1, A2 action is the Cartesian product of A1's own effects and A2's own effects. So you will get again pairs. Okay, and the idea of that is that if in fact this action is supported, if this meta action is supported, then its pair effects are also supported. Previously in the normal planning graph, just because P is present, Q is present, you are never sure whether PQ is present. Here you are essentially ensuring that if PQ is present, then both P and Q are present together. So in a particular level, you will have both P, and you can have both P and Q and PQ. Okay, it's sort of the proposition list then become redundant. So essentially, they have all the unitary terms, and you have the pairs, and they stop with the quadratic graphs. Okay, but essentially, some of the discussion today, quadratic graphs in essence get you the mutual exclusions, the binary mutual exclusions. Okay, if you want ternary mutual exclusions, there isn't any simple way of propagating ternary mutual exclusions in the normal idea that planning graph that you read in the textbook. However, you can do it quite easily if you do a cubic planning graph, where at every level you'll not only have A1, A2, but you'll also have A1, A2, A3. Now notice that writing this on paper is going to drive you batty, but the point is that in essence you are getting the same effect as actually doing mutual exclusion propagation. Okay, but while just propagating labels. Okay, this is so anyway, and I think that there is a later paper in 2009 by Patrick Haslam, who essentially, the paper has a nice little title. It says HMP is HPM. Okay, where P is the planning graph And HM for them, it turns out, is the family of heuristics that try to get you the correct distance for m tuples. So H1 would be 1 tuple, H2 would be 2 tuples, H3 will be 3 tuples, and so on. And H2 sort of corresponds to planning graph with mutual exclusions. So they kind of came to it from a different direction. It turns out when you do Markov-Decision processes, we will talk about dynamic programming and essentially the DP updates, the Bellman dynamic programming updates. And you can essentially think of planning graph from the point of view of approximating the Bellman dynamic programming updates. That's a different way. It's a slightly different way, but the effect is the same. Okay. So we are discussing mostly from the planning graph side. Haslam actually has done work more from the dynamic programming equation side, and so he has looked at it where, in essence, so the idea of HM heuristic is that it takes a set of literals P1 to P100 and it equates the cost of that P1 to P100 as the maximum cost of an M subset. Okay, so H1 corresponds to max heuristic. Right, H1 corresponds to max heuristic. So because you're trying to compute the cost of P1 etc. up to P100 and taking the maximum of that, and that will be the max heuristic. H2 corresponds to planning graph planning graph with mutexes and then doing set level, which will correspond to essentially the costliest 2 subset of this set. Okay, and if this is a 100 set, then clearly the correct cost you will get when m equal to 100. Okay, but everything else is a slightly better and better approximation of the true cost of this set. And what he was, and so he came up with HMP heuristics, which correspond to like planning graph heuristics with multiple, unary, binary, and ternary, etc. Mutexes. And then in 2009, he essentially figured out, independently it seems like, because he hasn't cited this other paper, of basically the idea of a polynomial planning graph. Okay, and so you can do, so the propagation of HM heuristics is more complex than that of H1 heuristics, because H1 heuristics just directly propagate labels. So what he was saying is, if you don't mind increasing the size of the planning graph, in essence actually, instead of thinking of it as increasing the size of the planning graph, a slightly more systematic way is to think of it as changing the domain under consideration, such that apart from the ground actions, you also have these meta actions which corresponds to pairs of actions. And they have their own pair preconditions and pair effects. Okay, and you are writing normal planning graph for this quadratic domain, or normal planning graph for the ternary domain, and so on. Okay, so anyway, that's, and in fact, to the extent you have a very good approach for doing normal planning graph based relaxed plan heuristics, and more interestingly actually, this particular piece of work got used again just this year in combining the landmark heuristics with this idea. Remember that, if you read the rest of that paper, and which we might actually mention it today too, there is a simple way of propagating the labels on the planning graph to get the landmarks. Right? But that landmarks, basically, it only gets certain sets of landmarks. So one of the things that it doesn't get are what are called conjunctive landmarks. So for example, on the way to goal, I would need to pass through states where P and Q are true together. Saying P is a landmark, Q is a landmark is different from saying PQ is a landmark. That means you are actually forced to pass through a state where P and Q are occurring together. Okay, and computing the conjunctive landmarks will give you almost sort of a high-level overview of how to do the planning. Okay, and there is a little paper in, I think, ECI 2010 this year, which is sort of also interesting because, we are talking bleeding edge right now. Okay, essentially people are working on the stuff that we're just talking about right now. So there's a 2010 paper which essentially takes a domain, converts it basically, p power m for in some m value 2 or 3 or 4, and then does the landmark propagation on that domain, and that on that transform domain, and they show that they can actually get much more effective conjunctive landmarks. For a particular example problem, for example, they show that the conjunctive landmarks with their orderings more or less pretty much tell you exactly the sequence of states that you would have to go through to get to the final solution. And then you can actually just say from here to here find a plan, from here to here find a plan, concatenate them. Right? And they actually show that as m increases, for example, then they essentially can get more effective heuristics. But of course, when you increase m, the cost of computing the landmarks is increasing, because the planning graph is a much larger size. Basically, as m increases, planning graph would be exponential in the size of m. Right? Okay. That's basically the connection. I will still look at what you guys have done just to get a feel for, at least whether the mutex is figured out by now or you're just listening to me. So make sure that you give it to me by the end of the class. But I'll just quickly go through the mutex discussion, and also today I want to connect it to, if you're trying to find the subgraphs of the planning graph that correspond to solutions, also gets us into doing planning as satisfiability, which is sort of a different idea for doing bounded length planning. It has some advantages, although it's not particularly, it turns out that planning as satisfiability is an idea that you want to understand, not because it's winning currently, but because it's probably the second or third best way of solving any kind of planning problem. In the sense, if you, let's say you now go from classical to conformant planning, okay, it might be easy to write a SAT encoding whose solutions correspond to correct conformant plans. And it will take longer time to figure out how to set it up as a progression or regression search with heuristics, effective heuristics. You understand what I'm saying? So it's a useful idea, planning as SAT, satisfiability is a useful idea. And it should not be too surprising that, especially when you take a planning graph and are looking for a subgraph of the planning graph that corresponds to a valid solution, that would be obviously a combinatorial problem. You can actually show that it's an NP-complete problem. It's at least in the class NP. Okay? The moment it's in class NP, it's not surprising that you can reduce it to satisfiability problem, because every problem can be reduced to satisfiability. Every problem in class NP can be reduced to satisfiability. Full planning cannot be reduced at in a polynomial time reduced to SAT, because SAT is NP-complete and planning is p-space complete. But bounded length planning, where you decide is there a plan of length k, can be in polynomial time reduced to a SAT instance, which can then be solved by the latest and greatest SAT solvers. Okay? So anyway, I'm assuming that you read this negative interaction stuff. One specific idea that I want you to think of really is going back all the way to the original planning graph thing, if I can get there. Okay. Right? So remember, we got from here to here in the original planning graph, right? That was the idea. Now the question, of course, is, now we know that this is giving an upper bound but not a lower bound. In the sense, if what you are looking for isn't even present in the proposition list, it cannot be achieved by that length plan. But if it is present, there is no guarantee. That is actually, suppose for example, if P and R are present, P and R are present here, except there is no actual state that is reachable that has P and R together. P is in one state, R is in another state. Okay, which is basically the problem you get in terms of, and so P and R become feasible ignoring interactions by this level itself. But they are actually only feasible together for the first time there. right? Because there is actually a state PQR where P and R are true together. Okay, so what you would really like to have is, if P and R is your goal state, you would like to say that its actual cost is 2, not 1. And by saying it is 2, you would have a more informed heuristic, which will actually do more effective search. Agreed? Okay, now the question of course is, now basically the reason I got this problem is, of course, I removed the boundaries for the states. So I can say to improve my, so if I get back somehow the boundaries, then I'll have no problem. But then we decided to remove the boundaries because of a reason, because this is totally upfront exponential cost structure. A different idea is I will remember no goods. Okay, so in some sense memos. You read memos in textbook, right, about Graphplan search. So memos and no goods are subsets of literals that cannot be made true by that level. Okay, so this one is telling you, the full projection tree is telling you goods. That means that exact subsets of literals that can be made true by that level. Okay, and this one right now doesn't have that information, which subsets. So I might, instead of decomputing that directly, I might say, give me subsets, the no good, such that if what I'm trying to look for, let's say P and R, is subsumed by an existing no good. Subsumed by an existing no good. Okay? Not subsumed. So what I want to say is, let's say I'm trying to achieve P, Q and R by this level, and I have a no good. These are all equivalent terms, no good, memo, mutex. For binary it is called mutex also. Okay, so if I store a no good called PR, now PQR, essentially PR is a subset of PQR. And I'm saying that you cannot do PR together. And so you obviously cannot do PQR either, because PQR is a harder goal than PR, and PR itself cannot be done. Okay, so one advantage is, if I have a big list of no goods, okay, and if I have a set which I am trying to find the cost of, one of the things is I can actually have no goods to be of any arbitrary size. They could be pairs, they could also be triples. Okay, and in fact, when you do memos, right, when you learn memos, memos are mutexes of larger sizes. Okay, so then the advantage is that when I'm trying to find whether, so I found, I'm looking for PQR and they are present here, and before I say yes, one is the cost, I check whether at this level any of the no goods that are stored already are a subset of what I'm trying to make true. If so, then I'm dead. Okay, and there are ways in which PQR can become undoable. In fact, one of the interesting things actually is, it's not just, no goods are not just pairs and triples, they can also be singletons. The way you construct the planning graph, you never put in a literal which is actually a no good in that level. But if you allowed everything to be present, then singletons will also help you figure out whether or not a particular literal is actually feasible by them. Okay, and the second point is that when I have a set, essentially I just need to check if any of these guys, any of the no goods, are a subsets of the set that I'm trying to achieve. If so, then that set is not actually achievable. Okay, and you could have a scenario where I actually have PQR I'm trying to achieve, and so there is no PR in the no good list. That means pairwise PQR is achievable. PQ can be achieved, QR can be achieved, and PR can be achieved. And yet PQR is present here, in which case it's not achievable again. Do you see what I'm saying? So the memos are actually constructing n-array mutexes. This idea of n-array mutex, where the normal mutex is a 2-array mutex. Okay, and then a literal that cannot be present at that level is a one array mutex. Okay, so if you think about it that way, then what I'm trying to do is I basically took this, approximated this, and then I'm trying to compute subsets, or at least list subsets that will definitely not be true at that level. And even if I give you just a partial information about that, your accuracy can only improve. You see what I'm saying? Okay, so that's what mutex propagation is doing, and then the advantage, just as rather than construct this whole structure and then construct this, you construct this structure directly. Similarly, rather than looking at this and then realize, hey, notice that P and R are not present in any state, let me put a mutex between them, which is kind of a dumb idea because you already spent the exponential time and you're recomputing this. What Graphplan essentially did is to say, start from the simplest inconsistencies that you can easily detect. What's the simplest inconsistency? If an action cannot be done at the same time as another action, then that's considered inconsistent. Now, when can two actions not be done at the same time? If their preconditions and effects are inconsistent. Okay? So, in particular, if I have, so that corresponds, that gets us back to the last set that I was looking at, and put that up again. So this is what this is saying. Apart, you want to also figure out what pairs, triples, quadruples, n-tuples are not feasible. And if you remember which are not feasible, then you can use that to improve your guess as to how costly it is to achieve that set. Okay, full-scale markup is costly, but it's actually easy to do two-array mutex computation by propagation techniques. Now what's interesting to understand is the Graphplan propagation does not give you every possible two-array mutex. It gives a subset of the two-array mutexes. Why? Because sometimes a two-array mutex in level k might depend on a 3 or a 4-array mutex in the level k minus 1. So if you're only computing two-array mutexes, then you will not say that this P and Q are mutually exclusive. In fact, one of the interesting things is the planning graph does not compute any size mutexes exhaustively. It doesn't even compute one-array mutexes exhaustively. I do know that certain goals that won't be feasible, certain propositions that won't be feasible are not even brought into the proposition list. But they also sometimes can be brought in. Okay, just because your goal is present in your final list doesn't mean it is actually feasible. And one of the other things to understand that idea that I just mentioned, which is that a lower mutex at level k might depend on a higher mutex at level k minus 1, is to just realize that irrespective of how many ever goals you have, let's say you have a 8-goal problem, you can convert it without any change to a new problem where there is a dummy action, okay? A dummy action whose preconditions are these 8 goals and whose effect is done. And your problem now is to achieve done. Not these 8 goals, just to achieve done. Now clearly, if these 8 goals the only way you can be sure that these 8 goals are actually achievable is if you consider at least 8 array mutexes, sometimes more. Okay, certainly that means that this done might actually come into the last level even though it's not actually feasible. Okay, and really what you're computing in this list is more and more no goods. If you compute more of them, you get better improvement in terms of accuracy of your assessment. If you miss some, that's okay. Which actually brings into mind a little later down today's lecture, what's the minimal list that you must compute? And thankfully the very minimal list is for any pair of actions which are inconsistent, you mark them inconsistent. That's all. And everything else is just details. Okay? Now that should bring us to the question of when can you say that actions are mutex? These are the rules. Okay, but let's just look at that. So suppose I have an action A1 and an action A2. I would say A1 and A2 cannot be done together if A1 has a precondition P and A2 has an effect not P. Okay, because then they can't be done together, because the order in which they get done will decide whether or not A2. Remember, when I say A1 and A2 set can be done, because this is really classical planning, all I am saying is that every serialization of A1 and A2 must work without any change. This is sort of like transaction serializability in databases. Okay, and I clearly cannot serialize these two transactions in any order, because if I wound up doing it this way, it will be fine. If I do it A2 first, A1 next, then I would get a different effect. Okay, so preconditions and effects cannot be inconsistent. And when I say inconsistent, right now, I only mean this requires P, this deletes P. Okay, and then I can also say preconditions and preconditions cannot be inconsistent. So suppose this guy requires Q, this guy deletes Q, this guy requires not Q, then that's like the mutually exclusive goals. One guy requires Q to be true to be doable, the other guy requires not Q to be true to be doable. There's no way they both can be done at the same time. Okay, so these are competing needs, and these are competing preconditions and effects, inconsistent preconditions and effects. These two are minimally required inconsistencies. Okay, that you need to order. Then beyond that, actually Graphplan also says, if you, this guy says R, this guy says not R, then they are inconsistent. That is strictly not needed. Okay, why? Because suppose this guy gives G, and all I really care about is G being true in the end. And the fact that A1 removes R and A2, A1 gives R and A2 removes R doesn't really matter, because they don't affect G. Do you understand what I'm saying? Okay, so the effect inconsistency is not really needed. The minimal required is precondition inconsistency, precondition effect inconsistency. Now, can anybody say why effect and effect inconsistency is used in planning graph?
To trim down the search space.
Yeah, but I mean, but for example, I can give you a great way of trimming down the search space. Everything is inconsistent with everything. Just assume so. All actions are inconsistent with each other. Then basically there won't be any search to be done, and you will say the problem cannot be solved, or that every state is infinitely costly. But unfortunately that loses completeness of search. Right? I mean, heuristic also should be actually admissible and complete. You know, the underlying search should be complete. So you should be careful. You should be careful about how many things you say are inconsistent. If they're not strictly inconsistent, you shouldn't say it. Okay. Now, what's interesting is it's actually a subtle reason as to why planning graph does this. In some sense, R and not R are mutex only if R is a goal, or R is a sub-goal at some point of time. Then you need to know whether R is true or not. Do you understand what I'm saying? You don't tolerate ambiguity about a detail if in fact that detail actually helps some other later action to take place. Otherwise, I don't care whether R is true or R is false. It's just an incidental detail. Since, however, mutex propagation in planning graph is being done without even looking at the goal, right? Do you understand that? You only look at the initial state. You don't look at the goals. So, in essence, you overdo this extra mutex propagation, and thankfully, all it does do is it is completeness preserving in a funny way. if there is a plan for solving the action, the plan for solving the problem for the original problem, where plan is defined as sequence of actions, then even if you do this mutex computation, even if you just mark this R and not R as mutex, it'll still be a plan. I mean, you'll still be able to find that plan. What you do not get, however, is if you somehow liked planning graph because it somehow allows A1 and A2 to be parallel, and you start saying what I'm looking for is not just a sequence of actions, but a sequence of sets of actions, such that the shortest plan should have the smallest number of, the smallest sequence length. So A1, A2, A3 is the first step. A4 is the next step. So it's a two-step plan. If I'm looking for step optimality, then planning graph will no longer be step optimal. Graphplan, the final Graphplan algorithm won't be step optimal, because if all I wanted was G, I couldn't care less whether A1 and A2 are parallel or not, and I should have left them parallel. By sequencing them, I essentially am assuming that R would be a goal eventually, which may or may not be true. Okay, so so this is interference, this is competing needs, and the other thing is this one. So now, assuming that you did these interferences, then one interesting question is, as I said, the way this interference information, this mutex information would be used is given a set of goals P1 to P10. I look to see the first level at which P1 to P10 are present, and no subset of them are marked mutex. And then I take the index of that level and say that is sort of the length of the plan. Okay, now of course you could talk about relaxed plan in this context, and I mentioned it already previously that relaxed plan in this context is a correct plan, and it will be actually NP hard to compute even more. Okay, but so in some sense what you're looking for is just the first level at which the set is present with no subset being marked mutex. Now, if the underlying planner is actually trying to evaluate the quality of the plan in terms of the number of actions but not the number of steps, then this approach essentially underestimates, because I could have a one-step plan which has 100 actions in the first step, and then I can also have another plan which is 2 steps long and it has 2 actions. And both are plans for the problem. I can easily set up such a goal. Did you see what I'm saying? So for example, I mean, since I said I can easily set up, let me show you that I can. Suppose I need G1 to G100. Okay, my domain has A1 to A100 giving G1 to G100, and none of them are mutex. And it also has B1 and B star, such that B star requires magic, B1 gives magic, and then B star then gives all G1 to G100. Magic being a condition. Okay, now for this domain, there is a single step plan which is of length 100 actions, and there is a 2-step plan which is of length 2 actions. Right? Okay, and the set level heuristic is going to miss the fact that the 1-step plan really is 100 actions long, because it says there is no mutexes, so it's all fine. Right? And if you really want a better approximation to the length, then you throw this idea, which is an extra piece of mutex, where you will essentially say at no level can I have more than 1 action done. Which means every pair of actions, every pair of real actions Remember that there are no op actions to in the planning graph. Those are fine. But every pair of non-no op actions must be marked mutex. If you do that, then in this case you will see that you will get G1 to G100 using this plan only in the 100th level. Whereas using this plan you'll get it in the second level, and so you will actually compute 2 as the true cost. You see what I'm saying? So that's an extra thing that's not present in the original planning graph idea. And in fact, I know original planning graph just assume that I'll just give you, since you are talking about satisficing plans anyway, I'll give you sequence of sets of actions such that every set can, any permutation of that set is good. And I'm saying that if you search in the space of sequence of sets of actions, you don't necessarily optimize the length of the plan. In fact, you can be arbitrarily away from the length of the plan. And I also said that because of this effect mutex that Graphplan does, it doesn't give you the optimal step plans anyway. Okay, and the reason this is all interesting is that when, in a minute we'll see how we can convert finding subgraph of the planning graph into a SAT problem. And then for a while there was an argument that SAT planners were not competing well with search-based planners. So if you can't compete well, remember I said, I think I told you this marketing rule that be the first in your category, and if you can't be first in your category, make a category where you are first in, right? And so SAT plan tried to be first in the category of all planners, and when the heuristic search planners are doing better, then what do you say? Well, actually I am first in the class of step optimal plans. And my whole discussion right now should have told you that step optimality is first of all bogus, because it's not enough, it's not clear that anybody really cares about step optimality. And secondly, planning graph doesn't give you step optimality anyway. Okay, so that's sort of a technical point there. Okay, so this is the minimum set. And of these minimum, actually just the precondition and precondition effect are the true minimum that you need to do. The moment you do that, you're done. Okay, but then precondition effect, and effect, if you do that, that's the minimum that Graphplan does as static mutexes, static interferences. After that, planning graph propagates these mutexes recursively. And the propagation rules are very simple. The idea is that, if an action A, previously action A requires P and action B requires not P, they would be considered mutex. But now, all I really care, that's because even before you started the planning problem, just from logic, you knew that P and not P are mutex. So you should assume that really you are in a logic where P and not P are not possible together. And that was just coded in, hard coded in. That's why A1 and A2 became mutex. But then if I also later on found that this is P and this is Q, and by static interferences I found, or some mutex propagation, I found that P and Q are mutex. One way would be that A1 gives P, A2 gives Q, nobody else gives P, nobody else gives Q, A1 and A2 can't be done together, so P and Q will become mutex. And so as soon as P and Q are mutex, then A and B are mutex. Because they require P and Q are cannot be done together, so A and B are mutex. In fact, this idea can be done in a much more interesting way, although this is what you do for binary mutexes. Suppose this requires P1 to Pk, and this requires Q1 to Qj, then as long as P1 to Pk union Q1 to Qj is a superset of any marked no good, the two actions can't be done together. Do you see what I'm saying? Because if any subset of P1 to Pk and Q1 to Qj are not doable, then these two actions cannot be done together. You might be wondering, what if the subset that I found is P5, P7? That only means that A can't be done. But then if A can't be done, and A and B can't be done together. Right? So it's sort of an obvious explanation. Okay, so that's one propagation rule. So two actions are mutually exclusive if they have competing needs. And two propositions are mutually exclusive. Two propositions are mutually exclusive if every way of achieving one proposition is mutually exclusive with every way of achieving the other proposition. So proposition mutexes are really sort of, they require a lot of work. For example, in this case it was simple because A1 is giving P1, A2 is giving Q1, A1 is giving P1, A2 is giving Q1, and A1, A2 are mutex, and nobody else was doing P1 and Q1, and so P1, Q1 are mutex. If you have A1 to AM giving P1, and so A1 to AM giving, A1 to A1M giving P1, and A2 to A2M, A2K, let's say, giving Q1, then you will say P1, Q1 are mutex only if each A1, each AIM is marked mutex with each AK, AJ2. And that's like, multiplicative number of mutexes. So when you find a mutual exclusion for two goals, that basically means there is no way of achieving it. You can't just say, oh, I tried for a while, I couldn't achieve it, so I assume they are mutex. That's not good enough. You exhausted all possibilities and there's no way you can make it true. So that's why, proposition mutex propagation is a stronger rule. And as I said, with this, then you will get binary mutex as the next level, which can then be propagated to the next level. And the propagation process itself is polynomial, and yet it's not complete because you are no longer you are not guaranteed that you will find all 2-ary. In fact, all even 1-ary mutexes this way. What it does give you is a better upper bound. If your subset, if your set of goals is present, but a pair of them are marked mutex, then it's not yet present. You have to go forward. Questions? Okay. Then, so, we look at this. I mean, I don't necessarily want to go through this, but here are mutexes over the Bloxworld problems. And you did some for the simpler problem. Okay. Now, level-based heuristic can be very easily expanded to planning graphs with mutexes. So you just look for the first level. You look for the first level at which the set is present and no subset is marked mutex. Okay, and if so, and that number would give you the length of the minimum length of the plan required to make those set of goals true. And it is admissible. It's guaranteed to be admissible. There is no shorter plan that you can ever find. Okay, and if you did serial graph mutexes, that means if you also wound up marking every pair of non-no-op actions to be mutually exclusive, then the number you get will be essentially closer to the real length. Whereas if it is step-based, it's faster to calculate because the planning graph, levels off much faster. Which actually also is an interesting question. What does it mean for planning graph to level off when now you have mutexes? Remember, in the previous case, planning graph level off meant two proposition lists and level I and level I plus 1 are one and the same. In which case there is no point in going any forward. But that's not enough here. Clearly you need to check that the mutexes also didn't change from level I to level I plus 1. Okay. Now this also makes you question, you come very close to it. Now for example, I'm trying to see if a particular goal set, P1 to P100, or P1 to P20, okay? The goal set P1 to P20, starting from an initial state, is that a solvable problem? That's what I want to know. Is it even a solvable problem? Now, if I didn't do mutexes and I drew the graph all the way to quiescence, and then if P1 to P20 was present in the final level, is it solvable? No. But if it's not present, is it definitely not solvable? Yes. Okay, so we could remove some of the problems that are unsolvable even with non-mutex propagation. Once you also do mutex propagation, you can prune out some more problems that are unsolvable. So you will come up to the level graph where I to I plus 1th level proposition list hasn't changed and list of mutexes also haven't changed, and yet P1 to P20 either are not present or present but some pair is marked mutex. In which case you know for sure that P1 to P20 is an unsolvable problem. Okay. By the way, where did you use the ability to prove that a problem is unsolvable in some recent reading you did? What? No. In the recent, in the paper that you read, right? You have to use this property that planning graph affords of detecting at least some unsolvable problems in a sound way. When it says it's unsolvable, it's for sure unsolvable. When it says maybe it is solvable, maybe it is, maybe it isn't. When did you use this? Yes?
To check ordering between landmarks.
And also to actually check whether something is a landmark. To see whether or not something is a landmark, the idea is, can I reach my goal state without, can I reach my home? So for example, you're sitting here and you're looking at the news and they say the following intersections, there were bombs and they closed them. And you're trying to see whether or not I should try to go home. Okay? If all these intersections, if any of those intersections is a landmark for you, or if the set of those intersections is a disjunctive landmark for you, then you can just order pizza and sit here because you can't go home. That was the point. But then you better have a proof. If your girlfriend or wife or boyfriend asks you, what the heck were you doing sitting at school when you could have come home? Because there is this other possible way of coming home. How do you prove to yourself that you cannot go home? Essentially, you say that remove every action that gives as its effect the landmark and see if the problem can still be solved. If it can be solved, then it's not a landmark. Okay, so you used this idea of unsolvability in landmarks. Okay, and the idea of unsolvability improves as you do mutex propagation. Now, even with the mutex, I can only say maybe solvable, but I can never be completely sure. Suppose I want a sound and complete procedure for checking whether a plan is actually solvable, a problem is solvable. And I want to extend this idea that I just given you. What do I need to do? So if I do mutex propagation, I'm able to catch some more problems that are unsolvable. So if I do 3-array mutexes, then I'll solve a little more problems. If I do all possible mutexes of all possible sizes, and I keep expanding the planning graph until from one level to another, no one of these mutexes, not of size 1, not of size 2, not of size 3, not of size 4, not of any size, can be rediscovered, can come in. Then you have a proof that if still in this final level, if it still is the case that P1 to P100, in this case P1 to P100 are present in the final level, they are definitely solvable. I mean, without any subset being mutex. So this is how you actually prove solvability and unsolvability with complete certainty. And in the textbook, I don't know whether the 3rd edition has it, but the 2nd edition had this proof of Graphplan's completeness. This is the completeness of Graphplan proof that I just gave you. Okay, which is surprising because in general, planar completeness theorems are hard to come by. Okay, so you are saying that if you keep expanding the planning graph and you use the old Graphplan method for looking for the subgraphs of the planning graph to find which is the solution. And whenever you fail, you are remembering the memos. The memos are no goods. And if between two levels memos didn't increase, then you have really reached quiescence. At which point you have a truly leveled off planning graph, and that can be used to answer questions of whether or not planning problem is solved. I'm not suggesting that you should ever do it at home, because it's basically worse than just trying to solve one problem. Okay? But that's the way you prove that there is definitely no solution. Okay, because any other thing, maybe if you did some more work, maybe there would have been a solution. This way, you know for sure. Okay. Okay. So that's level-based heuristics, and we also talked about memos idea. One interesting question is, so I can extend the level-based heuristic very easily, and it is admissible. Okay. How about extending the relaxed plan heuristic? Remember, we had a relaxed plan heuristic. Why don't I extend that? Now, to understand why we won't, and I'll come back to this in a minute, to understand why we won't, basically, you look at this animation, by the way, I drew. Okay? Although I said several animations I never tried, but this one is ours, mine, definitely, and just gives you an idea of how backward search works in planning graph. And the point of this is both to explain the original Graphplan algorithm in one slide, okay, and to point out why relaxed plan idea is a non-starter once you have mutexes. Because even finding something that I repeated already a couple of times before, even finding a greedy relaxed plan is NP hard. Forget about optimal. Whereas in the previous case, only optimal was NP hard, greedy was not. Okay, so here is my planning graph, and this is sort of, you can use this to understand how Graphplan search works, and it also can be used to understand a couple of other things such as improving memos, which is what actually I drew this picture for at one point of time. So suppose this is my little planning graph. I1 to I3 are true in the initial state, and the following actions are present in the next level. They give the following effects, then there's some more actions and some more effects. Now this is not a strictly correct planning graph, because obviously I1 should come here too, right? There should be a bunch of no-op actions that I should have put, but if I put all of them, it will become really busy and you can't see what's going on. Suffice it to say, what I removed, it doesn't affect what I'm trying to teach you right now. Okay, so suppose I want to, I did the, and you notice that I've already done some sort of a mutex propagation. Okay, and I have only for some reason been able to find that A6 and A8 are mutually exclusive, and A7 and A11 are mutually exclusive, and A5 and A9 are also mutually exclusive. Imagine they were mutually exclusive because of static reasons. So they have either competing effects, or competing preconditions and effects, or competing preconditions. Okay, so then what happens? And then I came up to this level and I found G1 to G4 is present in my planning graph. And right now they are not marked mutex. Assume that actually the reason I don't have any more mutexes here is because there are no mutexes to be actually found. That's okay. It turns out that it's very important to understand that if you did not propagate mutexes from level to level, but only ever made sure to mark just the static mutexes, then everything I'm telling you will still hold. And the propagation, all it does is it improves the search. So as soon as you marked all the static mutexes at every level, between non-no-op actions and no-op and non-op actions, then you're done. Remember that when I talk about static mutexes, if there is A2 which gives G2, and there is a no-op action which basically persists, not G2, then you have to mark those two as mutex too. That's also a static mutex. Okay, that's what I mean. Okay, but it's very easy. There is no propagation involved. Each level you just mark a bunch and then you can move on. Okay, but let's assume these are only mutual exclusions. Then if I have found that suddenly that G1 to G4 are present, no subset is marked mutex, So then I want to see if I can, either you can act either which way. Either I want to get a relaxed plan for supporting G1 to G4, or if you read ahead, want to get a plan, because relaxed plan in this case is also a plan, assuming I did all the static mutexes. Okay, then what happens? I got G1 to G4, and basically I supported G1 with A1, G2 with A2, G3 with A3, G4 with A4. Up to that it's simple. Now all of these will then bring in their preconditions. That's also simple. Now in some sense, making G1 to G4 true here requires me to make all these guys true here. P1 to P6 true. Agreed? Because G1 is being supported by A1, who would then require P1 to P3, P1 P to P3 at this level. A2 is supporting G2, which requires P4, A3 is supporting G3, which requires P5, A4 is supporting G4, which requires P6. So if you are banking on these guys to give you the 4 goals, then you better make sure these are true here. If this was the first level, then all you need to check is that these are present in the initial state, and then you're done. In fact, if this was the first level and you reached it, you're done, because nothing in the first level is mutually exclusive. Because first level proposition list is also a real state. Every other proposition list is a dummy state, it's not really a state. First level proposition list for classical planning is a real state. Okay, if you didn't reach the first level, then you recursively do the same thing you did here, except starting from here. Now what did you actually do here? Something that you took for granted here everybody is supporting, every goal is supported by just one action. Really what you had to do was pick a goal. These are sort of variables in the CSP terminology. Pick one of the goals, pick one of the actions to support it, then pick next goal, pick an action to support it, next goal's action to support it, until all goals have actions. And you want to make sure that the ones you supported just now, you picked just now, they are not already mutually exclusive. If they are already mutually exclusive, then you backtrack and change one of the choices until you find non-mutex choices at this level to support these guys, which will then spawn the preconditions at the previous level. Just because the choices here are non-mutex, unfortunately, doesn't mean the preconditions are satisfiable, because they can be actually because of the ternary mutexes, because of the higher order mutexes. It may still be the case that you have to backtrack. Right? Okay, but that didn't happen here. I came up to here, everything was good up to here. Then I actually do the search. And so for P1 I just take A5, okay, and then for P2 I take A6, and for P3 I take A7, for P4 I take A8, and as soon as I did that, A6 and A8 are marked mutex, remember? Okay, so then what I need to do is I need to redo this P4. In fact, I need to backtrack, and really what is happening is a CSP search, where this variable was given a value, then this one, then this one, then this one, and then the value you gave here was a problem, so you have to backtrack. If you have no better idea, you do chronological backtracking. And Graphplan, original Graphplan did chronological backtracking. And actually I drew this picture because at one point of time I showed that if you do dependency directed backtracking, planning Graphplan search can be significantly faster. And we'll actually see that in a minute. Okay. In general, what happens is that Graphplan's memos tend to be much larger than they need to be. So it winds up saying, well, I failed because at level 7, P1 to P100 cannot be satisfied together. But the real reason P1 to P100 cannot be satisfied together may just be that P25 to P35 cannot be satisfied together. And the moment that 10 cannot be satisfied, the 100 also cannot be satisfied together. And remembering the simplest reason for failure is extremely useful, because the simpler reasons will wind up being useful in multiple other places, and so it also allows the search to backtrack much farther up the tree. That's dependency directed backtracking. Anyway, continuing here, P4 supports A8 and that doesn't work, so I backtrack and I undo this choice and I give a choice to P4 supporting A9. I'm sorry, A9 supporting P4. Unfortunately, I don't have any good luck today, and A9 and A5 are dead. So it looks like P4 cannot be given either of its two values. Remember in CSP, if a variable cannot be given values, then that CSP problem is dead. So can I just say that I can go back now? Not yet, because it's possible that the reason P4 can't be given choices is in the context of the choices that were made for P1 to P3, P4 can't be given values. If you only know whose values to change and redo P4 again, you'll be fine. Now this is where the real backtracking happens. Up until now, the immediate variables, different value was checked. Now, this is where what you need to do, essentially in this particular case, what Graphplan would do, is since P3 was the last variable before P4, it will go and try to change the values of P3. I argue that that's a pretty dumb idea. Because the two reasons why P4 couldn't be given a value is once P4 couldn't be given a value because P2 was conflicting with it. Another time P1 was conflicting with it. So you could remember the conflict set, which is P1 and P2, and backtrack to the latest member of that conflict set. Now notice if these were 100 propositions long, the conflict set could have been the first and the third one. And you could have really backtracked all the way there, which is a very huge improvement in terms of search. And by not backtracking, you are undoing decisions that have no real bearing on the failure that you actually saw happening. It's like, the plane crashed. You found that the last thing we did was paint the plane. So the next time, don't paint the plane white, paint it red. And see if it crashes still. You see what I'm saying? That's exactly what you're doing. Chronological backtracking is the stupidest idea. But to do any better, you need to have domain knowledge as to what causes failures. I mean, if you guys are all laughing, thinking, paint changing doesn't make any sense, it's because you know how the world works. At least you think you know how the world works, and you're pretty sure that paints don't cause crashes. I could be living in a bizarro world where there are people with maybe our Afghanistan or one of these nice war theaters where people are looking for a particularly obnoxious color and they're shooting the planes out of the sky because they have that color. So for example, they won't like Southwest ugly red and whatever thing. So anytime a plane goes with that color, out it goes. So in that case, changing the paint would have been the correct idea for that domain. And if you ignore it and you say, no, planes should not be, planes don't go down because of color, then you're missing the point. Okay? The bigger issue is you explain a failure and you undo the parts of the current solution that are taking part in the explanation of failure. This is a very big point. You do this every day in your life. Even if you don't understand, like me, how cars work at all, you may know why certain things may not have any bearing on whether or not car will start. Right? And so, for example, if the car doesn't start right away, then I don't come out and start changing the paint of the car. Why? Because I know many things can stop a car from moving, but I don't believe paint is one of them. So that's like an upper bound on the explanation. So this doesn't take part in the failure, and so I skip over it and go to other things. Like, obviously, kicking the tires is always a good thing to do, right? Because because all of us seem to believe that if you kick it a bit, sometimes it starts. So that's part of our explanation, and that's a dumb domain theory, but it seems to work. Don't yell at a domain theory that works. Okay. So in this particular case, by not realizing that P3 was not part of, so the way normal Graphplan works is it will also backtrack over P3, then it will backtrack over P2, then it will backtrack over, and when it backtracks over P2, and then, so in this case actually what happens is, when it comes to P3 and tries to backtrack, there are no other values. So even though it was doing stupid backtracking, it lucked out because the problem was such that there is no other choices. So you wanted to change the paint, but they said it's regulation, only white paint is available. And so you can't change the paint. So you have to change something else. Okay? However, if there were like 18 other choices here, you would have tried all of them. And you would have recomputed these failures in multiple different ways. Okay? Anyway, so now you went up over P3, you went up over P2. P2 does have another choice, and then that is A11. So you try A11, and this time what happens? A11 winds up violating A7. So you fail again. Okay, now you have to go further up above P2 to go to P1. Now P1 doesn't have anybody else. Okay, so now what do? I say, who the heck asked me to do P1 to P6 here? The previous level. So ask them to change their mind. So in some sense, in terms of search, in the search tree, there is G1 level, G2 level, G3, G4, P6, G3, G4, P1, P2, P3, P4, P5, P6. That's the search level in the each variable in the search tree. And you're just chronologically backtracking. It just so happens that after every few variables, you're just changing the level. But the underlying search tree doesn't really care whether they're from different level or not. You know, if P1 doesn't work, it will then go to G4. Okay, and then so basically, and before it goes to G4, it realizes the following thing. I don't really know why I had to achieve P1 to P6. It could be that my mom asked me to achieve P1 to P6, or my dad asked me to achieve P1 to P6, or my girlfriend asked me to achieve P1 and P6. But I exhaustively proved that whoever asks me, I can't make it true. It's not that they didn't ask me nicely, it's just that it's impossible. Okay, so if I just prove to myself that this set is not doable here, I may as well remember this fact. So that if I ever need to make this entire subset true here, then I'll just stop the search right away and go back. So if my mom asks me today and then my dad asks me tomorrow, then I tell my dad, I already tried doing this yesterday and it doesn't work, so I won't waste my time. That's memo. Okay, and Graphplan remembers these memos while it's doing search, and then it'll come and redo the choices here and then go forward again. Okay, and so and obviously because there is backtracking, it's essentially an exponential problem. There is no polynomial time solution for it. In fact, you can prove that it's NP-complete by reducing an NP-complete problem to it. Not vice versa, I hope, because I'm also teaching ASU 101, which is for people who just get into computer science, and whole of last week and this week was saying, trying to convince them that just because they can reduce some problem to SAT problem doesn't mean that problem is hard. You can always reduce the easy problem to hard problem. To show the hardness, you have to show that the hard problem can be reduced to what you thought was an easy problem. Okay, so to prove that this is actually NP-complete, you can actually prove some problem. I don't know whether, obviously one of the NP-complete problems can be reduced to this, and that's why you prove it. But now that you know at least it's an NP-complete problem, and it's of course on the class NP, because if I were to give you a subgraph of this planning graph and say, hey, I think this is a solution, you can check it in polynomial time. So it's an NP problem. Okay? And so, since it's an NP problem, you can always, and it's also an exponential problem, you can always compile it down to SAT, and SAT becomes your RISC architecture, reduced instruction search set architecture for NP-complete problems. So, instead of everybody trying to find good heuristics for their own favorite NP-complete problem, let's all convert our problems to SAT, and then put a bunch of SAT people in some kitchen somewhere where they keep trying to improve the SAT solvers, which is exactly what they've been doing, because every year there's a SAT competition, and SAT solvers efficiency has been increasing significantly every year. That's really bothersome. Okay, and so the question then is, I just showed you how original Graphplan worked, and in fact I also showed you, I also sort of explained to you that although this whole thing is a memo, it turns out that you can actually argue that only a subset of these are a memo. And if a subset is a memo, then a superset of any memo is also a memo. If I can't do P1 and P2, then I can't do P1, P2, P3 either. And this idea that I was mentioning that I did many years back basically was to show that this same search can be easily changed by keeping track of the conflict sets, such that this is what's called essentially in CSP conflict directed backjumping. And if you do that, then you get smaller memos. Smaller is good. Smaller explanations of failure are always good. Right? I mean, it's like everybody is trying to figure out, and of course because we know that people like smaller explanations, sometimes we make fake smaller explanations. stock market went down because Beijing started selling some notes. That's probably a fake explanation, but we know enough people want small explanations, so we just give it. Okay, but on the other hand, the worst case explanation is stock market went down because if you take the weighted average of all the stocks in the stock market comprising S&P index, it just happened to have reduced in value. What is there to know? Then you don't feel very good at all, because you think you know more than what you did before. And the same thing for BP's problem. BP oil rig, as to why it broke down, we want to know. We want simple solutions, one paragraph solutions as to why exactly went wrong so that you can undo that. But if you just say the entire thing, the entire situation was the explanation of failure, then all you know is you should not repeat that entire situation again. So that includes if certain people are wearing, one guy was wearing a purple shirt and another guy was wearing a blue shirt on the fateful day, make sure nobody ever wears purple and blue shirts again. Or at least one of them would not wear one of those shirts. That way you can be sure that it's not the exact same situation. That means at least you would avoid this exact same failure, but there may be other reasons, such as, actually the oil cap isn't working and so you keep failing, and you will learn all of those also. So in essence, if the real reason for this memo's failure is these three, and you are trying to remember a 10-sized memo, then you're going to get a 2 power 7 versions of this memo. Did you understand what I just said? Because the 3 are the problems. And those 3, if you plan, the 10 can still be changed. True, false, true, false. So there are 2 power 7 configurations which have the offending 3 values set. And all of them would be learned as memos. Okay. The last thing I want to say is, so I said you could learn those smaller memos, but you can also say, who the heck wants to solve this planning graph using planning graph specialized solution? Why not just convert it into somebody else's problem and then go to sleep? Which is basically convert this into either SAT or CSP. And the way I explained this search, you should not be surprised that that can be done. Because really these are variables and they have values. So in particular, here is the SAT compilation. Okay, this essentially tells you what propositions and axioms you must write such that the model for this SAT theory would correspond to a valid subgraph of the planning graph. Okay? And this translation is polynomial time in the size of the planning graph. And then you give this translation to your SAT solver, and the underlying SAT solvers keep improving every year, so you can improve. You can solve subgraph finding of the planning graph much faster than actually keep writing better and better algorithms just for, much with less effort from your side than keep writing better and better algorithms every year. Because now SAT is your risk architecture, it's your substrate. So what are we doing? So this is a slightly different planning graph, but so there are some goals here and some actions before the previous level and some other goals, some other preconditions on which those actions are supported. And unfortunately, you can see this. Let me see if I can change the color. Okay, so these are, anytime I write something like this, it's a proposition name. I just made up a proposition name by essentially putting hyphens between, if you have at or e, then I write at dash r dash e, that's a proposition. Okay, so initial state would be a conjunctive formula corresponding to all the propositions that are true in the initial state. Goal state is a conjunctive formula that corresponds to all the propositions that you want to make sure are true in the goal state. So this already reduces the number of models. Whatever model you're trying to find must give true values to these, must give true values to these. The question is, what are the constraints? How are these connected to other variable values? And now what you do is, the next question is, I need to write down this graph structure as a set of SAT axioms. All I need to do is essentially, if I want a condition to be true at this level, I want at least one of the actions supporting it to be true in the previous level. Remember, actions also correspond to action propositions. Conditions correspond to condition propositions, actions correspond to action propositions. So, for example, in A1, remember all these propositions are going to be indexed with respect to the level. So if in A occurs in the first level, it will be called in A1. If it occurs in the second level, it's called in A2 and so on. And none of what I'm saying would change if I start thinking of them as G001, G008. All that matters is the connections between the variables. So in A1 implies load A1 because only in A1 is only supported by load A1. Okay, and in B1 implies load B1, and at RM1 implies fly R1, and at RE1 implies plane at RE1. Okay, now what is plane at RE1? At RE1 implies plane at RE1, that's just a persistence action. That must be true. Now, obviously, this is a simple problem. In fact, if there were two actions supporting in A, then I would have said in A1 implies this or that, a disjunctive formula. If I do this for everyone here, and then I do the same thing for everyone here, okay, then I have got the graph structure from here to here. The other thing I need is, if an action is to be true, its preconditions have to be conjunctively true. So all I'm saying here is load A1 implies at RE0 and at AE0, because both its preconditions must be true. All its preconditions must be true. So this is the propositions to action axioms. These are actions to their precondition axioms. If I do these, then I have already completed the planning graph structure. The only thing that is remaining is the one piece of information that's in this graph that I didn't write down yet is the mutual exclusions. Right, I might say two actions are mutually exclusive, or two propositions are mutually exclusive. Well, I can write that. Okay, so for example, if I want to say P and Q are mutually exclusive, how do I write that? It's either not P or not Q. That's it. So for every mutex action, I will write those mutual exclusion constraints. Okay? If I do that, I have a large big SAT theory. I feed it to a SAT solver, and I will find the solution. The interesting thing is, in the beginning when they tried this, one big problem that occurs is SAT theories normally right now are still declaratively represented. They are represented explicitly. So the size, the very size of the file that is generated can be gigabytes large for a large enough planning graph. And a last story I just want to mention.